Class, welcome to Module 2. You should have already reviewed the difference in difference lecture video. That will be helpful in going through this first, and then you can move on over to the supplemental PowerPoints. This one will be brief. We're just going to be discussing hypothesis testing with dummy variables. And I'll have you each know that when I took this course, all I received was the PowerPoint, and I had to read through it on my own, and in some parts make heads or tails out of it, which is not as easy unless you have some description about what exactly it's talking about. So hopefully this helps. As always, if you have any feedback or suggestions, if you feel the videos were helpful, if you feel they should be different, modified, please let me know. I'd love to make this course as um, successful as possible in terms of helping all the students learn the material. So please let me know if there's something different we can do with these recordings, but hopefully they can serve to help translate the information to you in a more successful way. Now, jumping into it, this is first going to be looking at, sorry, let me get my drawer out. We're going to be, for the next several slides, we're going to be looking at some information, some data, and talking ultimately about hypothesis testing with the dummy variables, which was covered briefly in the lecture, and then talking about an example where we're working with Teach for America teachers wanting to, which is it's a program for non-education majors to become teachers. And generally those TFAs, as we're going to refer to them, are working in, sent to work in low-income schools. And that's going to be compared against regular teachers, which are students who went to college to become a teacher. So their coursework was on becoming a teacher versus TFAs where they were not previously trained to be teachers, becoming teachers. And again, we're going to be controlling for suburban and urban environments. So depending on the type of school, typically urban schools would be low income compared to their counterparts, suburban schools, which are higher income. So that's a control we're going to want to pay attention to. We're looking at math scores for these groups. So we have our regular teachers, Teach for America teachers, TFAs, and their scores, their students' math scores as a percentile in suburban environments and urban environments. And we're going to go more into that here. So we can see this data frame is a dummified version where each individual observation has a dummy variable representing what group it is a part of, where we have our TFA in suburban schools, our regular teachers in suburban schools, our, sorry, our TFAs in urban schools, and then our regular teachers in urban schools. And color coded as well. We'll be seeing this for a few more slides. So ultimately we have 10 TFAs, 10 regular teachers. However, 11 teachers teach in suburban schools and 9 teach in urban schools. So we notice a little difference there. So let's look at the difference between suburban school scores and urban school scores. So we can see that kids do better in suburban schools compared to urban schools, which would generally be uh, theorized if we were working with this problem. Now, if we're just using averages, let's say we want to compare the group averages for teachers. So we want to compare them as TFA instructors, their group average, and regular teachers as their average. If we were to just do it as you see here, we would see that the averages are the same. So your TFA instructors have the same average math score as your regular teachers. So we would then say, is Teaching for America or Teach for America, is this effective? There's no difference. But ask yourself, think about it for a moment. Would you actually trust these results, or do you believe that somehow bias has been introduced, or there's something we're not accounting for? Well, if you were wondering that, if you thought that the school type is a big indicator, you'd be correct. Just looking at the averages, it doesn't control for the difference between the urban schools and the suburban schools. So now let's look at it a little bit more granularly. We have our TFA instructors in suburban schools, and we find that among those, when we group it this way, the score is 75, and regular teachers in suburban schools, when we group it this way, the average score is 75 as well. So that we can see fairly simply that in suburban schools, there's really no difference between TFA instructors and regular teachers. However, when we do the same thing, but look at urban schools, and sorry, the PowerPoint's wrong, so it's been this way for years. Just leave that off. That's supposed to be urban. When we segment these by teacher and by the urban school, we can see that TFA instructors, their average math scores for students within urban schools is actually 66, compared to regular teachers in urban schools only 57. So there's a 9-point spread between TFA instructors where they appear to do better than regular teachers in urban schools. So now, why is it that we get this difference? Or sorry, why is it that we can't tell the difference when we compare them directly, but we can see it here? And it's really just because the proportions of teachers that teach in urban schools is different than the proportions of teachers that teach in suburban schools. Regular teachers are more likely, 7 out of 10, 70% of them are regular teachers in suburban schools compared to 60% of TFAs teach in urban schools. So there's simply a weighted difference where TFAs, they have more lower scoring observations compared to regular teachers. So the regular teachers are weighted more heavily because of the regular suburban school. The scores are higher, so that weights their average to be higher. And the Teach for America instructors, they're weighted on the lower end because they have simply more lower values because they're more likely to teach in urban schools. So really the difference appears to be not the teachers, when we're looking at it this way, but the school environment. Except for urban schools, TFAs do better. So if we were to just look at it this way, we would incorrectly conclude that the TFA training program is not working when it actually is, and not working meaning that it is not different from the regular teachers. So moving into some more dummy variables, once again, this is everything grouped independently as we've seen. Now this right here, I don't want you to get caught up in this. Um, this is just showing that it's going to be different than how we would need it for our diff-in-diff model, because if you were to run a diff-in-diff like this, where you have all the observations ungrouped, you would have an issue with what's called multicollinearity. And you'll learn more about that, but ultimately the RLM function would drop the groups that have issues with multicollinearity. So this just leads us into why we would need to group, and like we learned in lecture with diff-in-diff previously, this works with group means. So we aggregate all this together and we have our group mean for each group. So we have the group mean for the teacher America, which would be the teacher America in the suburban environment, the 75 value. And then we have our suburban regular teacher value here, 75, that's our group mean, and then so forth, 66, or over here too, I guess. Okay, so now we're going to be looking at what is essentially our coefficient table we looked at in lecture, but it's set up a little differently here, and it really just kind of demonstrates what I mentioned before, the additive nature of the coefficients. And very important, this is a little different than how we talked about it before, where we had a control group, treatment group, and then we had a pre and post treatment measurement. So in this, we don't necessarily have a clear intervention date. Uh, so just to know, in case you get lost, when I went through this on my own and tried to make heads or tails out of it when I was taking this class, I did get a little caught up on putting all this together because it doesn't translate perfectly from the lecture. I believe the end of this PowerPoint does go through something that involves a treatment group. We'll cross that bridge when we get there. But just know that when it comes to how you set up your model, it will still work the same. The interpretation just changes. So the thing I want to really point out is right here, in the way this model set up, we established our reference group, classified as the intercept here. And again, that's where 1 is toggled on for the intercept and 0 is the rest because it doesn't apply to these groups. So this intercept column represents our urban Teach for America teachers, or math scores for those teachers, which would be the 66. So beta 0 represents this group. The reference group in this situation is the urban Teach for America math scores, 66. This is the actual average. Now, continuing off of lecture, it's additive in nature in the sense that if we want to determine average for our other groups, we would have to do some adding depending on what we're looking at. So for our beta 1 is representing the difference, and beta 1's here going to be the suburban group for Teach for America. This is representing the difference between the urban TFA and the suburban TFA, and we can see that suburban schools with the TFA instructors, they do 9 points better. You can see that here as well. Now, if we wanted to look at the urban schools specifically and the difference between the regular teachers and the TFA, now we're looking at beta 2. And again, that's one because of how this is set up, where we have our intercept being the urban schools. Well, urban schools with Teach for America, but it's representing the urban schools. So when we want to look in the urban schools, we want to toggle on regular teachers. So that's going to be this one right here, this 57. Sorry, it's the average, my apologies. The difference is -9, though, also seen right here. So if we want to determine the average score of our urban schools with regular teachers, we would add our beta 0 to our beta 2, which would be 66 minus 9, giving us an average of 57. Measures right there. So our urban schools with regular teachers do worse than, in this situation, our intercept, which is our urban TFAs. Okay. And then finally, the beta 3 represents our counterfactual. Once again, the difference between what we would expect without a treatment or intervention and the actual treatment or intervention. So the difference between the counterfactual and the actual value. And that's going to be additive of all of these. So this is going to represent 1, beta 0, plus beta 1, plus beta 2, plus beta 3. And that'll ultimately give us the value of 75, which this guy is recognized as the suburban schools with regular teachers. Okay. Now moving on the next few slides, it's going to jumble this. It's going to jumble how you set up the model. Don't get confused. You can change it to be how you want. So no matter how you change the groups or which one you omit, as it's called here, turn it into the intercept, as long as you know what your reference group is, you can still do the math and determine what the average scores are, or recognize and interpret what the changes would be. So in this example, it changed the reference group to be the suburban schools regular teachers. Our beta 1 represents the difference between suburban schools regular teachers and urban schools TFA teachers, and we can see that the coefficient is now -18. But still, we get the same values. We just need to know which coefficient represents which in order to interpret it. So this is pretty straightforward once you understand what you're looking at there. Again, just changing the reference group. You can still get the same results. It's just a different way. It'll just change the coefficients themselves, but it still represents the change in comparison with the intercept. Okay, moving into hypothesis testing, I'm going to ask you to review. Let me pull it up here. The section in the lecture right here that discusses how each coefficient really represents a hypothesis. Beta 0 is the hypothesis would be is the average outcome of the control group before treatment different from 0. Hypothesis for beta 1 is the difference between the control group and the treatment group before treatment different from 0, uh, so on and so forth. We'll go over it more in here, but this is the um, area that's pertinent to this upcoming discussion. Now, this page here, this is saying, why don't we just run the model as this, where we just have each group with a dummy variable? Um, it's intuitive, but why don't we want to run it this way? And ultimately, it's because these coefficients would then be looking at the hypothesis of, is it different from 0? And is 75 different from 0? Yes, it's different from 0. So are each of these values different from 0? Yes. So our research question is whether teachers trained in TFA, Teach for America, who went through that training, if they perform better than teachers trained in the regular traditional format. And none of these tests, if we were to model it this way, test for the significance of coefficients beta 0 to beta 3. In this regression, it doesn't tell us anything. So this model would actually not be able to give us the information we're looking for because we already know that the group means will not be 0. So this little visual here, this goes over the hypotheses that are tested with each coefficient. So referencing this are our Group A, suburban schools with regular teachers. Is that different than Group B, which is our urban schools, regular teachers? So are regular teachers different depending on the school? For hypothesis 2, we're asking within urban schools, is there a difference between regular teachers and the TFA instructors? For hypothesis 4 here, the difference between D and C, we're saying within Teach for America teachers, do the TFAs that teach in urban schools and the TFAs that teach in suburban schools, do they differ? Are they different from 0? And then here we're asking for hypothesis 3, the difference between TFA teachers and regular teachers in suburban schools. And then you also have your regular teachers in suburban schools. Are they different from urban schools with TFA teachers and so forth? But ultimately, that's what these are looking at. We're asking, is there a difference? And that also is why our coefficients don't represent the values themselves. They represent the difference, the chain. So if you're like me, I get a little caught up, or I got a little caught up, pardon me, when I was in this class and I was reading through this once again without any kind of audio to help explain it. I was just reading this, trying to make heads or tails out of it, and it got a little confusing because the lecture clearly talks about groups that are control groups, treatment groups, like my horrible visualization here. We have our control group, let's say, we have our treatment group, let's say, and this is our XY axis. Don't judge me once again. And I was just caught up because I didn't have like a clear delineation line of pre-treatment, post-treatment in this example. So I just want to tell you, don't get caught up on that. Just focus on the fundamentals here of really we're looking for differences between groups. And so depending on how we set up our model, that'll determine what these values represent. So circling back here once again, I believe this is the same one we had looked at before, but it's more talking about how we're really testing hypotheses. So what we're asking is if beta 0 is it equal to beta 0 plus beta 1. If beta 1 is equal to 0, then there's no difference. If it's different from 0, then there is a difference. So in the example of suburban TFA, is it different than urban TFA? We'll be looking at our reference group, which is the urban TFA, average score of 66. And then we have our suburban TFA, which is beta 1. So we're going to be asking, is beta 0, intercept here, different from beta 1, which is the suburban schools with the TFA instructors? And we can see, yes, there is a difference. So therefore, beta 1 is not equal to 0. So there is a difference. Sorry, that was a bit redundant, but ultimately that's what that's looking at. Once again, you'll see this ultimately just testing different things. So is beta 2 equal to 0? No, it's not. We know that because beta 2 is representative of TFA teachers in suburban environments. My apologies. Urban urban environments with regular teachers. So my apologies. So beta 0 urban TFAs, and then beta 2 is the difference between regular teachers and TFA teachers within urban environments. So we're just checking these hypotheses. Hypothesis. You'll hear me say it multiple ways. Now, moving into the counterfactual, once again, the counterfactual is represented by beta 3, which would be the change that we would, or the difference, excuse me, between the change that we would expect and the actual change. As represented here, this looks a little bit more like what we saw in lecture 2. Let's call this our X and Y axis. We have our beta 0, our pre-treatment comparison or control group value. The change for post-treatment for the comparison group being represented by beta 2. Beta 1 representing the difference between the pre-intervention control group and pre-intervention treatment group. And then beta 3, in addition to all of those, all coefficients added together, represents the actual value we find for the post-intervention treatment group. The removal of beta 3 would tell us what the value of our counterfactual would be. So the hypothesis we're testing here is whether the treatment was effective or not. If it's different from 0, it was effective. So if beta 0 plus beta 1 plus beta 2, our counterfactual, is different from beta 0 plus beta 1 plus beta 2 plus beta 3, then we know that our treatment had an effect. Or another way of looking at it visually, pardon me, is the difference between these. So we can see this is where we would, excuse me, we would expect it to be if the parallel trends assumption was occurring. If both groups, control and treatment group, were expected to change at the same rate, then that's where we'd expect it to be. And how spread apart this would be, the actual outcome would be, excuse me, from that counterfactual. That's our beta 3 value. So if our treatment had no effect, we would see our D here, our post-treatment treatment group outcome, be the same as that or equal to that, or ultimately beta 3 would equal 0. Okay, so now this is a little bit more in line with what we had gone through in the lecture, and this makes a little bit more sense. At least it did for me once again when I was taking this course. So if, let's say we want to look at whether a diet pill works the same for men and women. So just to read through it, men and women in the study are randomly assigned to treatment and control groups. Measures are all at the end of the study after 6 months. So let's look here on the left. In blue, we have our control group. Our male control group has an average of 180 pounds per person. And our female control group, their average weight was 40 pounds or 40 pounds lighter than men. Looking at the treatment itself, we have our treatment group for the men. The average weight loss was 10 pounds. For women, they ended up at 130 pounds. So again, a 10-pound difference. So men go from the control group to the treatment group. We can see that there was a change of 180 pounds or 10 pounds, excuse me, between the male control and the male treatment. And we can see that for women, there was also a 10-pound difference. So we would have expected then the same trend using parallel trends assumption that women would have a similar trend, and that would be the counterfactual at 130 pounds, which is the same as our actual treatment group. So therefore, beta 3 is equal to 0. Our treatment had no effect. And to clear anything up, if that was confusing at all, this right here breaks it down. So just review that as well to see what each represent. But ultimately, that's what we're looking at with our counterfactual. And if we determine that the beta 3 is equal to 0, and then of course 0 means nothing in our regard, so we can just leave it out, and our model can simply be beta 0, beta 1, and beta 2, or just look at the treatment group itself, the difference between the group flag, pardon me. Now, if it were a different outcome, same scenario, but a different outcome, we have our female treatment group. Their outcome was 125 pounds, but we expected them to be 130 pounds. So we can see that the beta 3 is different from 0. Therefore, it has an effect of an additional 5 pounds of weight loss. So we can say that the the diet pill, pardon me, has a larger effect on women than on men. And now if the results change to be as such, our beta 3 is equal to 10, but our treatment, forgive me, I had to step away for a moment. So coming back to where I was, I'm going to repeat myself because I lost where I was, folks. So this example is looking at if there's differential effects for men and women. So once again, beta 0 represented here by our male control group um, intercept. Uh, sorry, the final weight of men in the control group. Um, Here, this is our interceptor. Everything thereafter is all based on a change from this value. Mark that as beta 0, terrible drawing. Then we have our beta 1 represented here by the change uh, in the male treatment group compared to the male control group. So we can see that men lost 10 pounds between the control group and the treatment group. Beta 2 represented here, this is the difference in the control group between male weight averages and female weight averages. And beta 3 representing here the difference between the female control group and the female treatment group. And we can see again, beta 3 is equal to 10. In an instance like this, we have our treatment. Now in this example here, we're looking at a differential effect for men and women, where once again we have beta 0 representing the male control group average weight, beta 1 representing the change in men from the control and the treatment group, beta 2 representing the difference between the male control group average weight and the female control group average weight, and then beta 3 representing the change in female control group average weight and the counterfactual that we would have otherwise expected. So men lost 10 pounds, assuming the same trend, we would assume women lose 10 pounds. However, our beta 3 is 10, showing that there is a difference between the female control group and the female treatment group, indicating that the pill has no effect on women because their weight remained the same. The counterfactual would otherwise be that the trend is the same, that men and women both react the same or similarly to the weight loss pill, or it's equally effective. However, we see here that it is completely ineffective for women because the slope is 0. And so ultimately in our equation here, if we were to math it out, we would simply remove these two values because they cancel each other out. So our male treatment flag, or our treatment flag, sorry, for pre and post, um, and our female treatment flag. So if our observations are both treated and female, this would be on. Um, this would be representing our male treatment because our intercept is male control group. This beta 1 would represent our um, male treatment group, so 1 or 0, depending on if the men are treated or not. So for all women, this would be 0. For female, this would be toggled off for all men, 1 for all female. And then our treatment female interaction term, this is referring to the treatment, or sorry, only women who are in the treatment group. So to circle back, just because I don't want anybody getting lost in the weeds on that, let's see if we got a good example. We need to go. This could work. It's not as straightforward as I'd like it to be. Bottom line, okay, and for this example here, since I didn't recap it. Okay, moving on into an example that might make a little bit more sense because we have a control group, treatment group. Um, this is what we're looking at. So we have the context is we're asking the question, does a diet pill work the same for men and women? So they're randomly assigned to a treatment and a control group, and they're all measured at the end of 6 months. Um, so we have, to clarify our assignments, we have the beta 0 intercept. Let me get my drawer out again. The beta 0 intercept is representing our control group average weight for men. So the average weight of men in the control group, sorry, the final weight of men in the control group. So these are the placebo group. Then we have beta 1 representing the change between the male control group final weight and the male treatment group average weight, which we can see is -10, reduction of 10 pounds between the control and the treatment group. So we can see that there is appears to be some effect, at least on men, with this diet pill. And now our beta 2 represents the difference in the final weight of women in the control group. So beta 2 here, we can see that the final weight of women, they have a 40-pound less baseline for the control group at the end of it. Now we want to compare that to their final result for the treatment group, or those who actually took the diet pill, as represented by beta 3. Beta 3, I guess I'll write it here too for good measure. So beta 3 is 0, therefore we can determine that the pill, it works the same for men and women, so there's no difference. And that's, remember, just it represents what we're asking and how we set it up. So just pay close attention to that. Um, but the counterfactual that we want to focus on, uh, we can see that if we stick with the trend, the parallel trend assumption, we would assume that men and women would have the same slope. And so our parallel trend assumption would be that women would lose 10 pounds the same as men. And in this case, they did. So we can see that our treatment actually had no effect because there is no difference between the counterfactual and the actual outcome, and the beta 3 is equal to 0. So we know that is not an effective treatment, or there's no difference, excuse me, in the diet pill for men and women. So same scenario, but let's look at it just a tiny bit differently. And sorry, before I jump ahead, this is just saying that very simple math. You can simplify your math by, instead of, if beta 3 is equal to 0 and you want to determine the post-treatment weight of women, you can just leave off beta 3 and do the math for the counterfactual, which once again is this. Or you can add in a 0 and it is still the same because beta 3 is 0, at least in this outcome. Now, going into that different example, so everything is still the same. So we have our male control group, which represents the placebo group, um, and the average male weight in that at the end of the treatment, so the end of the 6 months. That's going to be our beta 0. We have our beta 1, which is the change in weight between the male control and treatment group. Beta 2, which is the final average weight for women in the control group. And then last, we have beta 3, which is the difference, the Diff-in-Diff estimator, which shows the difference between our actual outcome and the counterfactual. So going with the counterfactual, once again, we would assume that male and female would have the same trend. Therefore, we would expect females to have an ending weight in the treatment group of about 130 pounds, assuming that the weight loss, the diet pill, worked the same for both. But in this case, we actually see -5. So we can actually determine that the diet pill has a greater effect on women than it does on men by a magnitude of 5 pounds over the 6-month period. Now, same thing once again. In this example, we have beta 0, beta 2 here, beta 1, and then we have a difference where we can see that the counterfactual would put it at 130 pounds, that women would lose the same amount of weight. However, our Diff-in-Diff estimator, beta 3, is 10, showing that our female treatment group at the end of the intervention is 10 pounds more than our counterfactual. Not 10 pounds, not that they gained 10 pounds, but that they are 10 pounds more than we would have expected using the parallel trend assumption. So in this, we can determine that the pill has no effect on women. So we can answer our question, does it work the same? No, it does not. It works on men, it does not work on women. And once again, just seeing this visually, pardon me, the beta 3, the Diff-in-Diff estimator, tells us the difference between the counterfactual and the actual outcome. And that's going to be the treatment female, so the interaction term between treatment and female, which if we were to look at this in a data frame, this would be only female and only the treatment group, they would be marked as 1. So that interaction term is what identifies that and tells us the difference on how the diet pill works in men versus women. Now, circling back to the original example with the Teach for America instructors compared to regular teachers, so as we've gone through, we've seen a few different ways to arrange our model, and the ways that we arrange it help us to answer the question that we're seeking. So depending on how you want your results to be interpreted, you can arrange this in such a way. For instance, in this example, we can recall earlier that we noticed that suburban schools, the difference between regular teachers and TFA teachers was non-existent. However, the difference between TFA instructors and regular teachers in urban schools, it was different. So really, how we want to set up this model helps us to determine which questions we want to ask. So if we were to use the regular suburban teachers as the reference group, that allows us to answer the questions in our study because the two hypotheses are about we are about are one, do TFA teachers perform better in suburban settings? And do TFA teachers perform better in urban settings? So we want to see how TFA teachers perform in comparison to our reference group suburban teachers. So we take our baseline, which is your traditional teacher representing our intercept, beta 0. So we have their score. And then from there, we're determining the differences based on suburban, urban, and Teach for America teachers. So let's see, where's our beta 1? I apologize, another item needing to be addressed. Beta 1, this is labeled beta 2, but it should be beta 1. So we take our intercept, that being the average scores for regular teachers in suburban schools, and then we want to look at regular teachers in urban schools and see the difference. And we can see that our value is negative 18. So regular teachers in suburban schools versus urban schools, those outcomes will be negative 18 points different in the math percentiles. Now, beta 2, this is going to be telling us if there's a difference between TFA instructors and regular teachers in a suburban environment. So that's going to be representing the hypothesis C here. Sorry, I skipped over that previously, but this is telling us ultimately whether TFA teachers do better in suburban schools. So let's do a little connect the dots. Beta 2, let's do a little connect the dots here. Pardon me, folks, I had to step away briefly. We have a newborn and he decided to start crying. So thank you for your understanding. Okay, so forgive me to recap where we were at. We're looking at the hypotheses that are tested with each coefficient. So easily labeled here, we have A to B. A to B, the way this model set up, is representing the difference between regular teachers in suburban and urban environments. So regular teachers in urban versus suburban environments, are they the same? Are they different? That's what this beta 1 is testing here. Beta 2 is going to be testing the difference between suburban regular teachers and C, which is our suburban TFA. So is there a difference between TFA and regular teachers in a suburban environment for beta 2? And then finally, beta 3 tests the difference between our counterfactual, the summation of beta 0, beta 1, beta 2, and our actual outcome, which is the summation of all of our coefficients. So once again, beta 3 is not a direct test of group means B equals D. It's a test of D equals counterfactual. So we want to know is the performance of a TFA teacher if there's no difference in urban schools. Sorry, folks, once again, I had to step away briefly. Coming back to it, I forgot where I left off, but ultimately the point is are D in this scenario. The beta 3, the hypothesis it's testing, it's not, it's ultimately looking at the difference or testing whether the counterfactual is the same as our actual result. So I don't want you to get confused. Going back to the example with the diet pill between women and men, we can see that even though our beta 3 had an effect, this is not saying that women gained 10 pounds. I don't want that to be confusing. It's not that women went up 10 pounds because it's a positive 10 value. It's that this is the difference between what we otherwise would have expected. Okay, so it is not a direct comparison between the female control group or beta 2 and, or sorry, the intercept, forgive me, the combination of those, it is simply the change of what otherwise would have been. Okay, so it's really important to interpret that. Beta 3 will always be representative of the difference between the counterfactual, what we otherwise would have expected, had the trends remained the same, and the actual result. Okay, so that should do it for this video. Go ahead and jump on to the next, and I'll meet you there.